Hey guys, so today we are starting lesson 7.1, chemical names and formulas. So in this lesson we're basically going to be learning how we're going to name compounds depending on the type of compound that we're talking about. Obviously we have many different types of compounds and not all of them follow the same rules for naming. Alright, so first thing we need to talk about is something you probably already know from previous years, is that when I look at a compound like this, the little number at the bottom tells me how many of each atom I have. So when I look at a molecule like octane, I know that this octane molecule has 8 carbons and it has 18 hydrogens. And this is what an octane actually looks like. So if you count them, you'll see that there are 8 carbons and there are 18 hydrogens. Okay, so this basically tells you how many atoms of each one you have. All right, next thing we're going to look at is something that looks a little bit like this. Some of you might know what this is, some of you might not understand, but our basic idea, you guys understand that there are 2 aluminums, right? 2 aluminums, not very difficult. You can also tell that there are 4 oxygens and that there's 1 sulfur. Now guys, I want you to remember that just because there's no number here doesn't mean that there are 0 sulfurs. In chemistry, to make things simpler, anytime we have to represent the number 1, we just don't write it at all. This is why there's 1 sulfur and 4 oxygens, and this whole thing together makes a sulfate ion. All right, so this is actually aluminum sulfate that we're looking at. And when I look at this little 3 on the outside, you kind of wonder what's it doing there. This basically means that there are 3 sulfates. So there's a compound within a bigger compound. And I have 3 of them and 2 aluminums, right? So if I was going to look at this whole thing and I want to figure out exactly how many oxygens are in my entire compound, all I would have to do is 4 times 3. So I know that I have 12 oxygens in my overall compound. This is because I have 3 sulfates and each sulfate has 4 oxygens. So let's take a look at this. This is aluminum sulfate. I can see that there are 2 aluminums and there are 3 sulfate ions, right? Remember the polyatomic ions that we talked about in our previous lesson? These are some polyatomic ions. So you can have more than one of them in each compound. Okay? So let's take a look at how well balanced this compound is. We see that each aluminum has a charge of positive 3. Each sulfate has a charge of negative 2. See, -1, -1. So overall, they have a charge of negative 2. If I look at this aluminum, the positive 3 is surrounded by 3 negatively charged oxygens. Then I look at this aluminum that has a charge of positive 3, and it's also surrounded by 3 negatively charged oxygens. This is because negatives are attracted to positives, and in an ionic compound, we are always looking for balance. So the number of positive charges has to cancel out the number of negative charges. So let's see if the overall thing is balanced. I can see that I have overall 6 positive charges and I have 1, 2, 3, 4, 5, 6 negative charges. So my overall charge of the entire compound is 0. And that's actually what makes it stable in this form. All right, so now we already know that when an atom gains electrons, we become an ion, an anion, which is a negatively charged ion. And when an atom loses electrons, you become a cation, which is a positively charged ion. And if it helps you out to remember this, cations are positively charged. Remember, cats have paws, okay? It's just a weird way to remember it, and anions are negative. I don't know, they're the other one. Okay, so when I look over here, I see that this nitrogen has 5 electrons in its outermost shell. It's missing 3, so it has the potential to gain 3 electrons and become negatively charged. But in gaining those 3 electrons, it doesn't just become negative, it becomes -3, right? It does this because to fill its outer shell will create a nice stable noble gas configuration, and it has a nice full octet, so it becomes stable and happy, right? So we go from a nitrogen atom to a nitride ion. We're going to get a little more into that in a minute. And then we know that that's a common thing that happens for a lot of atoms, but there are some atoms that actually prefer not to give away or take electrons from anyone. So a good example of this are carbon and silicon. They actually prefer to form covalent compounds. So they're kind of an exception to a lot of the rules that we're going to be talking about because they don't want to give away electrons. They would rather go and share. That's because they're kind of right in the middle. Like they can gain some, they can lose some, but they would prefer to share them, okay? So they don't want to form ionic compounds, they want to form covalent. So let's try to figure out why. This is going to be a very useful periodic table that you're going to use throughout this entire lesson, maybe for the next 2 weeks, and it's just going to be very helpful. So the basic idea here is that when you look at the charge above the group, it tells you what charge the general group is going to have. So if I ask you, when a potassium becomes an ion, what charge is it going to take on? I would go and I would find potassium is right here. It becomes +1. If I asked you, for example, nitrogen, it's going to become an ion. What charge is it going to carry? -3. Bromine, it's going to become -1. Aluminum, +3. And these are just general trends. Obviously, in some cases, things do change a little bit, but these are the trends that I want you to follow for now, okay? Things will get a little bit more complicated later on, and I'll tell you when to change out of these trends, okay? But you do need to understand this because there are going to be questions that basically expect you to just already know what the charge of these things are, and we're not always going to be explaining to you how to find them. All you need to do, open this periodic table, figure out where your atom is, and figure out which charge it would carry. And as you guys can see, the noble gases have a 0 on top because they are not willing to take or give away any electrons, just like we've been talking about all term, right? All right, so now we're going to get into naming monoatomic ions. A monoatomic ion is an ion that is made up of a single type of atom. So for example, if lithium became an became an ion, that would be monoatomic. But when we were talking about aluminum sulfate earlier, that was not monoatomic, right? That had a lot more going on in it. So potassium, when it becomes an ion, basically it's called the exact same thing. Cations don't change their name. So the potassium atom has the same name as the potassium cation. It's just potassium cation. Magnesium, when it's an atom, it's called magnesium. When it turns into an ion, it's also called magnesium. Really, nothing changes about the name of an atom when it turns into a cation. And you know that this is happening mainly in the first 2 groups of the periodic table. This is why we're talking about main group elements. Just remember that the transition metals have their own weird set of rules, and we're going to get more into that in a couple of days. All right, now things do change a little bit when we're trying to name ions. So in cations, the name of the ion stays the same as the name of the atom. But when we're talking about an anion, the name of the ion actually changes. So right here, F is for fluorine, right? When fluorine gains an electron and becomes negatively charged, we drop the end of their name and we replace it with "ide." Okay? So instead of fluorine, it becomes fluoride, not fluorine-ide. You have to actually get rid of the end of the name and add "ide" instead. And for example, nitrogen, we literally get rid of almost its entire name. We get rid of this ogen and we add an "ide" instead. So we go from nitrogen to nitride. And if we had oxygen, we would go from oxygen to oxide, chlorine chloride, bromine, bromide, etc. You get the idea, right? And remember that the only ones that are actually going to become negatively charged and become anions are going to be in this general area, the nonmetals, right? And you can even see that on the periodic table that we gave you earlier. Negative, 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 and pretty much the entire rest of the periodic table has a tendency to become positive, not negative. Even these ones down here that are more in the metal zone would not technically follow these trends. All right, so let's just look at this. Here we can see the names of main group cations: lithium, beryllium, aluminum. Literally nothing about their name changes. Their charge changes, their name stays the same. And then we get into the anions, and we can see that their name does change. We drop the end and we replace it with "ide." Fluorine, fluoride, chlorine, chloride, bromine, bromide, iodine, iodide. Get it? And you can use this as a reference to help you remember, but honestly, these are very easy to remember, so it's not going to be that difficult. And then we get to the D block metals. This we're going to get a little bit deeper into it later on, but when you get into D block, almost every single one of them is going to become positively charged, definitely not negatively charged, but they have different ways of changing their charge. So for example, if you look at iron, iron can carry a charge of +2 and a charge of +3. So it's going to be named in a different way than these guys are named, right? Because they follow different rules, and we're going to get more into those later. All right, guys? So now you're going to go and you're going to do the quiz, and good luck, guys.